Last time we solved the Schrodinger equation for single electron atom or a single electron ion, and let's really review some of the aspects of it. Maybe introduce some language, some of talking about these. But we found the solution to the Schrodinger equation, in which the Hamiltonian operator operates on a wave function, quantum mechanical wave function, that in this case is in spherical coordinates. And if you operate, then you get the energy times that wave function back again. And in our case, we're looking at the Hamiltonian that has this kinetic energy operator and has this piece here, which is the potential energy operator. This is just simply the potential energy of an electron in the presence of a nucleus that has a plus ZE charge, and that's sort of the picture that I look at here. Uh, so that ZE minus E, orbiting about it, say in radius r, so it's going in a nice orbital model. And then the nucleus is plus CE and minus E. Of course, there's an attractive force that keeps it going in this circle, and so we've got a bound state here. The solution that we found here, mu is the reduced mass of this nucleus electron system. We gave those last time. But what we found was for the solution was an expression that looks like this. These are the states of this electron. And we found that it reduced to a radial wave function, this r n sub l r, and we gave some of those anyway, times an angular portion that is just the spherical harmonics. And the eigenvalues of this equation up here, E is called an eigenvalue of H. For this system, we found this really a set. The energy levels are given by this expression, minus z squared 13.6 electron volts over n squared. I remember this one. Z is squared, that's the atomic number here. And then I remember for hydrogen, the Z is just 1, and this becomes 13.6 electron volts or thereabouts. N is a quantum number that goes from 1 to 3, so we see that energy is not continuous in quantum mechanics in this case, but is quantized in these very discrete values for the energy of the electron. That's the total energy of the electron in this bound state. We also had the angular momentum, square of the angular momentum, was also quantized. It could only be in h bar units of h bar squared. H bar has units of angular momentum, and so L and L plus 1 times here gives us the total square of the angular momentum. And for the wave function to be normalizable, the L's had to take on only the values discrete from 0 all the way up to n minus 1. So once you're looking at a particular energy level, maybe 2 up here, then if n is equal to 2, then L will go 0 and 1. 2 minus 1 is 1, so you just have 0 and 1. So usually you pick the energy level, then you know the L values associated with it. And then the M sub L's, likewise, as the Z component is quantized, M sub L H bar. And M sub L goes from, the way I like to write it, 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. So once you know you're in a particular L state, then M sub L can take up all the values all the way up from 0 to plus or minus L. Really more precisely what we have is the following. We've been able to find a representation of the quantum state of this electron that it simultaneously is an eigenvalue of the Hamiltonian, the angular momentum operator squared, and the Z component of the angular momentum operator. Remember, physical quantities are operators in quantum mechanics. And so uh, the energy here, E sub n, is said to be an eigenvalue, so sometimes you'll hear of that. It's always a number here. The eigenvalue is always a number. And the wave function that we get the eigenvalue times it back again is the eigenstate. In this case, the angular momentum squared operator has the eigenvalue h bar squared L times L plus 1. And our wave functions that we developed are also eigenstates of the momentum operator squared, as they are for the z component. Uh, and the m sub L times h bar is the eigenvalue of the angular momentum operator L in the z direction. I'm sure, just to recall, I'm sure you're more familiar with this from previous classes, but n is called the principal quantum number, and it takes on values 1, 2, 3, etc. L is usually called the angular momentum quantum number for obvious reasons. Takes on values 0, 1, 2, all the way up to n minus 1. So whatever the value n is, we're limited here to what this goes to. And then m sub L is generally called the magnetic quantum number, and it takes on this range of values. And sometimes people will write it, it goes up in integer steps from minus L all the way to plus L. And sometimes people like to write it that way. And I'll write it both ways, depending on the context. It's called the magnetic quantum number because it's related to some magnetic properties of the atom. So maybe go into a little later. So each quantum state of the electron, so these we're getting the wave function of the electron in the atom ion single electron atom ion system, is characterized by a unique set, at least up to this point, of quantum numbers n, L, and m sub L. And just to summarize, the allowed values are these. How these arise is because it has to satisfy the Schrodinger equation, the wave function does, the psi does, and that wave function has to be normalizable. So it has boundary conditions, and it turns out these boundary conditions do not let every value of energy arise, but can only certain discrete values, which ultimately presents itself in these quantum numbers. So the quantum numbers associated with the system are a purely quantum mechanical effect, and hence the name quantum mechanics. Well, again, just to review a little bit, I'm sure you know that spectra corresponds to light emitted when an electron makes a transition from a higher level state, principal quantum number m, to another lower energy state, which I designate as n here. So n and m are both principal quantum numbers. The electron is initially up in the upper level, the higher level, and then it somehow or another makes a quantum jump down to the lower level. N always has to be less than m. And in so doing, it releases a photon of energy. Okay? And the way I generally write these, sometimes I'll just write it delta E, but I usually like to write it delta E as m goes to n. So the quantum number for this electron goes from m spontaneously down to n. This is delta E. Delta, anytime I write a delta, I'm always talking about the final value minus the initial value of this E. So this is, the final value is n, so that's En, and the initial value of E was Em. And we can plug in the formula that we had for those energy expressions. And get this expression for the energy. So as you might expect, as the energy goes from a higher energy level to a lower, it loses energy, the electron does. So the energy loses this amount of energy. Notice n is a smaller number than m, and so this number is bigger, so this thing in parentheses is positive, and so this overall negative sign is indeed the sign of E. So it loses energy. It's negative because it loses energy. But since energy must be conserved, this is one of the fundamental laws of the universe, uh, it is conserved by letting all of this energy go into creating and emitting a photon of this amount of energy. I usually call this delta E a photon. It's the one that's going to be h times the frequency of the photon, or hc over lambda. And all of the energy that was lost by the the system up here gets gained by the photon minus a minus up here just removes this minus sign, and I get a positive quantity. So in effect, you have this the whole system, the electron plus the photon goes the energy lost by the electron is delta E, and that's a negative number, and the the energy gained by the photon is exact opposite of that. That's actually a positive number, so negative plus positive of equal quantities, and the total energy doesn't change, so energy is conserved in this process. So the long and the short of it is that I can take this photon energy, hc over lambda, and set that equal to the minus the energy lost to make it positive that the photon gained, and we get this expression. And you may have seen that. Usually you solve this for 1 over lambda. You get some constants on this side, but ultimately people usually write it in this form. Z squared out front, and then R is sometimes just this lump parameter of everything not including Z. That's the constant, these fundamental constants out front. And that's called the Rydberg constant. And it's roughly this value here in terms of reciprocal centimeters. So this whole side has to be in reciprocal centimeters, and that will give me the wavelength in centimeters if I solve for it. Now, as we said, m has to be above n, and so if in the lower level state is 1, 2, 3, etc., then m has to be one of the numbers that's higher than whatever the value of n was. So it has to be at least one level higher, since m has to be greater than n in this picture. I usually look at it sort of pictorially to remember all of this. I have an electron up in an excited state, upper level, so m is bigger than n, and it spontaneously, for some reason, makes a quantum jump down to this level En, but in so doing, it releases a photon of wavelength lambda. Well, the long and the short of it is that these single electron atoms and the energy levels displayed by our solution are in excellent agreement with the line spectra observed for hydrogen and lithium ion, etc., i.e. for single electron, either atom or ion. Unfortunately, that's the last of the exactly solvable problems, for the most part, that you're ever going to get. So we'll see what happens as the story continues with the next segment.